All right, hello everybody. In this video, I am going to talk about what IEEE 754 encoding is and how to go from a a decimal number, so something like 87.562 uh, into binary. So representing this into binary, and this is a little bit different than just going from like 87 to binary, which is its own procedure, and we're going to kind of use this, but we're going to be amping it up uh, specifically in a different format. So without much other, stuff going on, I'm going to go ahead and bring up uh, this little thing that I've made. So first, let's just talk about what a float is and how that compares to an int. So if you remember, an int is going to be a whole number. So something like this over here, right? This 87, that's an int. Has no decimal, it's a whole number. We like ints. If you followed any of my other videos where I talked about basic Java programming, that kind of thing, but even past Java, right? Just in computer science as a whole, floats are going to be decimal numbers, right? So they hold this decimal, and so that makes them a little bit different in the way that we work with them and the way that they're stored in memory. So, again, that's what it is. Ints are storing whole numbers and floats are storing decimals. But there also are some similarities between floats and ints. So one of the first ones is that they're primitive types. So if you remember, strings and all those other things are reference types, whereas, ints, doubles, floats, booleans, they're going to be primitives. So floats also fall into that category as well. The other similarity is that both floats and ints are 32 bits in memory. And we're going to compare this to a double later on. And so, the 32 bits thing is going to make sense, as soon as I show you this, just because that's going to put into perspective what that actually means. So if I look over here, right, this is an example of how the IEEE 754 32-bit float encoding actually works. So I'm going to just let you soak this in, and I'm also going to be explaining the different parts. So let's just small that. All right, cool. So first thing over here, we have the sign bit, and this is under MSB, aka the most significant bit. And the most significant bit, the way that this works is, let's say that I have a number like let's call it 10,002, right? Like that. So over here, this one, isn't really a one. This is 10K. Okay, excuse the handwriting. And this two over here, well, that's just a normal two. So you see how the presence of this one is much more significant than the presence of this two. If I were to say, oh, do you want $10,002 or $10,001? You're not going to be too upset about that. You'll be like, hey, dude, I'm getting 10 grand for free. Why not? But if I come up to you and I say, you want $10,002 or do you want $2? You're going to be like, what kind of question is that? Of course, I want the 10K. So that's why it's the most significant bit. And over here, that's going to be the left side. Same thing over here. And 0 is for positive numbers. And for negative numbers, we're going to go ahead and use 1. So there's the sign bit. Now we go to the exponent. So it's the next 8 bits or the second to the 9th bit, if we're going to count left to right. And this holds the exponent value, including the bias. So if you remember how exponents work, like in scientific format, scientific notation, we're going to be taking the mantissa or the rest of the number and kind of multiplying that to the exponent value in a way, and you'll see this as we go further through this. Due to the bias, this will never be negative. And so we're going to talk about the bias in just a moment, but I just want to emphasize that throughout this video because that's something that is important, and there's a reason behind, there's a method to the madness. There's a reason why it exists. And then there's also this, again, like I've said, we're going to use this exponent to shift the mantissa. Cool. Now let's talk about the Mantissa, however you want to pronounce it, I'm not sure. So it's going to be the remaining 23 bits over here. It's a pretty big chunk of memory, or even chunk of the actual 32 bits. And there is this implicit 1 included, and I have a star to that statement right here because that kind of has some edge cases, and we're going to talk about that as well. And this is the value that, again, you're going to be really working with and using the exponent on. And so when we go through the example later on, this will all make a little bit more, much more sense. So now let's talk about this bias thing that I kept referring to. So this is included so that you never have a negative value for your exponent, right? So if you could imagine, if I go back over here and I have 0.005, and I want to represent that in scientific notation, well, that's going to be 5.0 times 10 to the negative. So notice how that's a negative, and we're going to shift over 1, 2, 3 times, right? So 10 to the negative 3. Well, you see how we have this negative over here? That could be an issue because let's say we omit that negative. Well, that's going to be actually equal to 5 and then shift it 3 times. 1, 2, 3. 5,000 is much different than 0.005. And so because of that, we need to include a bias, because otherwise, if we keep a negative value in here, we're going to need to waste one of these bits over here to store whether this value is negative or positive, right? As we've done over here with the sign bit. And you're already working with 32 bits. Realistically speaking, that's not much memory, that's not much space for you to work with. And if you're going to go out and start wasting space by allocating bits for signs and whatnot, that's not really necessary. You're going to be wasting a lot of space and a lot of efficiency. So in the CS world, that's that's a big no-no. So the idea is that we're going to add a bias so that this value is never going to be negative. And so what that does is, if you have a positive number, right? Let's say you have the positive 3, you add that to the bias, you're going to get a positive number, but a really large positive number. Alternatively, if you have a negative number, you're going to add that to the bias, and that's going to lead you to have a positive number, but it's going to be a really, really small positive number. And we're going to go through this in the example as well. And so for IEEE-754, the bias is, drumroll please, 127. That's the magic number over here. 127, that's just because of 8 bits. So realistically speaking, you're not going to be able to get any value greater than this. And so that makes sure everything is going to be positive. So let's talk about some edge cases, right? Because I'm sure a lot of you are thinking, are you sure this is a foolproof thing? And I'm sure, but that's because of the existence of these edge cases. So the first edge case is 0. So this is where the Mantissa, all 23 bits, are going to be all zeros, and the exponent, all 8 bits, are going to be zeros. The sign can be anything, and that's where this plus or minus comes into play. But basically, this means that the value stored in this chunk of memory is going to be 0. It could be positive or negative, and that's dependent on the sign bit, but that doesn't really matter because positive 0 is the same thing as negative 0. And if you don't come from a CS perspective, you might be a little confused with what is positive and negative 0. It's just, how computers work, but at the end of the day, 0 is 0. So the second edge case that we have is a no leading 1. And so if you remember, I talked about something called an implicit 1 for the Mantissa. And that could be a little dangerous, right? Because if you think about it, right? Let's say I have a binary number 1011, right? And so putting that into scientific format, I'm going to get 1.011, which is cool. If I have a 1 over here, so that's going to be an implicit 1. We're in business. But what if I want to store this number? Well, this is going to be 0.011, right? And let's just say that I need to have it in this format. I'm sure, realistically speaking, you could just do 1.1, but let's just say for the example, we need to store it like this. Well, in this case, I don't have that, implicit 1 in front of the dot. So that's gonna turn this value and interpret it as this value when I decode it eventually. So that's pretty dangerous. So the smart people that came up with all this came up with a kind of construct, right? Because if you think about it, if you're going to save another bit of the mantissa that's dedicated to a 1 or 0 based on the first bit, you're wasting space. So what they did was, and again, the whole idea of the implicit 1 is to save an extra bit so that we can use that towards a more accurate number, right? So what we do over here is, let's say the exponent is all zeros and the mantissa is not 0. That means that the mantissa does not have the assumed implicit 1. And so these two cases, 0 and no leading 1, are going to be your most common ones. But it's also important to talk about these other two, which is infinity and NaN. So infinity is where the mantissa, 23 bits, are going to be all zeros, and the exponent is all ones, so it's going to be the largest number possible. And so what this means is it's going to be positive or negative infinity, and this is again based on the sign bit itself, right? 0 positive, 1 negative. And finally, not a number or NaN is where the mantissa is not 0, but the exponent is all ones, right? And so infinity was where the mantissa was 0 and the exponent was all ones. Not a number is the exponent is all ones, so that's constant, but the mantissa is not 0. And so this basically means that the number is invalid or doesn't have a value yet. This is kind of dealing with some software or like some real nitty-gritty like basics that you'll dive into, like not basics, but really getting into what a computer is. So I really doubt you're going to be running into this on the daily, but again, it's something to keep in mind, something to be aware of. So, I've been blasting about all this other stuff, but let's see it in action. So I'm going to go ahead, work through an example with you, and we are going to be encoding 94.625 in IEEE-754 encoding. So I'm going to piece it out by going through the sign, the exponent, the mantissa, and then we're going to, at the end, put it all together. So sign is relatively easy. 94.625 is a positive number, so therefore the sign bit is 0. Cool. We are 1/32 of the way there. Now, if we look at the exponent, things start to get a little hairy. So first, let's convert the number, so 94, not 94.625, to binary. So that comes out to be 1011110. And I've outlined the math down here, but I'm not gonna lie to you. You can just take my word for it. And then we're gonna go ahead and encode the decimal part. The reason why I split this up is because the decimal encoding is a little different. So over here I have 0.625 times 2, which gives me 1.25, but I keep the 1, use the 0.25 for next time. 0.25 times 2 is 0, and 0.5 times 2 is 1 plus 0, so we get a nice 101 over here. And you might have cases where you don't have a number that divides evenly into 2 like that, or not divides, but multiplies and ends with a clean 1.0. And in that case, you're going to have some kind of repeating procedure going on. And so we piece it all together, we get 94.625 as 1011110.101. Cool. So now we want to find the number of times we need to shift. So this is again similar to scientific format, scientific notation, where if I have 94.625, I'm going to write that as 9.4625 and multiply that by 10 to the 1 or just by 10. Same thing over here, we're going to take this huge number and convert it to 1 point and all this and shift it 6 times. Notice how when I'm writing in decimal, I do times 10 to the first. Here I'm doing binary, so times 2 to the sixth. If you're given an exam or something, this is like a test question, don't make this mistake. Make sure that you're shifting in the base that you're given. Technically speaking, this kind of mathematics could be applied to octal or hexadecimal or anything like that. So technically it would be 16 to the 6th, 8 to the 4th, stuff like that. But just be mindful of that. Don't blindly just go at it. That being said, now we know that the exponent is 6, but do not forget the bias. It's a little tricky, I know, small points that you could miss, but we're gonna get through it, I promise. So again, the bias is 127, add that to 6, we end up with 133 or 100101 in binary. Cool, we have the exponent. Let's move on to the mantissa. So now that we already have the actual, thing, the actual 94.625 kind of in a condensed decimal form, what we're going to do is we're going to remove this implicit 1 that I was talking about earlier because it's there. And now we're left with this value, which we're going to just get rid of the decimal and be left with this. And so we're going to then normalize this number, and we're going to do that by adding trailing zeros. The reason why we're adding trailing zeros is because, well, if you think about it, this is a decimal, right? So 0.5 is the same thing as 0.50000. So that's what we're doing here. We're using up all the bits that we have, and anything else that we don't have, just because we do need to fill the 23 bits, we're just going to slap on a bunch of zeros. So over here, now we're going to piece it all together, right? So we have the actual order is going to be the sign bit, the exponent, and the mantissa. But it's not just, any mantissa, any exponent. It's going to be the biased exponent and the normalized mantissa. And I've kind of reflected that down here by saying, okay, 0 as the sign, 133 in binary, which is the biased exponent over here, and then this with the trailing zeros as the mantissa. So putting that all together, this is our 32-bit number, which works out to be 94.625. And as a final check, because why would you trust me? I'm just a random guy on the internet making a video about this. I've gone ahead and brought up a calculator that I've used for prior assignments, so I know it's valid, and put 94.625 in the calculator, and let's see what we get back out. So the number is huge. I'm not going to read it out loud, but you can see we have a bunch of trailing zeros, which is pretty consistent over here. We have a sign bit of 0, 0, and then we start off with like 1,000. I think it's like 10,000 or something. Yeah. And so feel free to pause and see if I'm right or wrong. But I hope that this little review and this example really helped you out in understanding IEEE 754 encoding. And if you have any other things that you would like to have me do or explain, just drop them out in the comments. Thank you.